Okay then, so let's move on. So this I have given a hopefully provocative title, Reducing First Order Logic to Propositional Logic. Yeah, I mean, can one do that at all? If you can, why have all these quantifiers and stuff? It's an interesting thought, and let's see how that goes. So this is a kind of interesting idea, I would say. Fairly non-trivial stuff. So what we'll do is, I'm not going to go into lot of the finer points of this, but this is more to give you an idea of how this goes, and actually to give you some insight into how modern theorem provers and software that tries to work with theories, first order theories, actually work. So yeah, okay. So first thing to note is something that I'd probably forgotten to do earlier. So this is one which is what is called Prinix normal form for first order logic. Prinix formula is said to be in Prinix form said to be in Prinix form if it is of the form q1 x1 to qk xk alpha, where alpha is quantifier free and qi belongs to for all that exists. You say that a formula is in Prinix form or prefix form, as some people call it, if all the quantifiers occur to the left. So you don't have quantifiers occurring freely, you have pulled out all the quantifiers to the left. So that you have, I mean, they can come in any order. You might say there exists x for all y, there exists z, there exists w for all u, for all v, and then a formula in all those variables. Yeah. So obviously, since you call it a normal form, the statement is that given any formula, I can rewrite it into Prinix form, preserving equivalence. That's why you call it normal form. Now, how would you do that? Any idea? So given any formula, obviously this is the statement. Given alpha, there exists beta in Prinix form such that alpha is equivalent to beta. So yeah, how would you expect to prove something like this? It's a fairly straightforward thing if you think about. I think we have done what is necessary for this in our exercises early on. It's just that I forgot to point out. So let's see. First, get rid of yeah, implication you can always write in terms of disjunction or conjunction. Yeah, and if and only if you could write in terms of a conjunction of two implications, therefore you can. So you can always do that. Another thing that you can always do is push negations inside. Again, how do you do that? If a not is standing in front of there exists, push it in, turn it into for all not. Not for all is there exists not. Not of and will give you negation inside with ors. Not of or will give you, yeah. Not will can be knocked off, in fact, and so on. So you can always push negations inside until they appear only in front of atomic formulas. This is all propositional, and we have seen. What about quantifiers? So this is the deal, right? So now, after having done that, what have you got left? Only conjunction, disjunction, and quantifiers, right? Now, how do you push or rather pull quantifiers out of these things? Well, there are certain validities that you can use, right? Maybe I'll get back to this later. There are lots of validities that are of use. We know this, for instance, right? Yeah. For all x alpha and beta is equivalent to for all x alpha and for all x beta. So if it is of this form, you can always pull it out. Similarly, you know that there exists x alpha or beta yeah. So that's also okay. What if you've got for all x alpha or for all x beta? You can't do that, right? Obviously, because remember, for all x p or not p holds, px or not px, but it doesn't mean for all x px or for all x not px holds. No. Similarly, there exists a conjunction. You cannot distribute. But then what you can do is you can always rewrite it, right? So for all x alpha or for all x beta is actually equivalent to for all x alpha or for all y beta with because x is bound here, x is bound, you can always rename. Is that clear? And once you do that, you can always pull it out. And in fact, this is generally true. And similarly, can also realize that there exists x alpha and there exists x beta is equivalent to there exists x alpha and there exists y beta with x replaced by y, where y is something not occurring. Otherwise, you will have some bound variable capture or something like that, y new. Yeah, you can always rename your variables so that. Is it clear what I am saying? Please tell me if it is not. So, in general, this is true. Q2y alpha, maybe I'll write it bigger, some Q1x alpha, Boolean operation, Q2 y beta is equivalent to Q1x, Q2y, and that's it. So this allows you to rewrite as you like. Yeah. So after pushing negations inside, the next step is this is something that people call standardizing apart. Basically this. What does that mean? If you have a subformula Q1x alpha, Q2y beta as subformulas, x is not equal to y, right? If you have subformulas occurring like this, right, rename them to make sure that, so whenever you see some qx sitting as a subformula, that there is only one occurrence of every such quantifier. You don't have there exists x sitting here, there exists x sitting there as well. Just rename them so that variables are all apart, and no variable occurs both bound and free. You don't want nonsense like this. px and there exists x, q, x, y. If you wrote something like this means this occurrence of x is free, this occurrence of x is bound. Why should you have something like this? You might as well rewrite it to px and there exists z, q, z, y. Yeah. Is it clear? You can always do this. You can always standardize apart the variables so that every quantifier occurring in the formula occurs exactly once, right? Every variable quantified, if there exists x appears, it appears only as there exists x in the entire formula, right? So you sit and rename all the variables, and after that you just apply these and you are through, right? And you know this alpha, this also is true, right? What else do I want? I'll write op here because it doesn't matter. Alpha op beta if x does not belong to, if x doesn't occur free, you can always put a quantifier and pull it out. So all this says that you can just keep doing this again and again and you can get it in Prenex form. Okay. So it's very convenient to then consider your formulas to be always in the Prenex form. This is one thing to make use of. Any questions about this? Maybe I'll do one example too. Yeah. Okay, here is an example. This is one. Just some cooked up thing, huh? Yeah. So first thing is to remove the implication, rewrite it as not of this, not of which will be for all y, not r x y, or there exists y s x y, or there exists y uh, okay, and then you remember what we said is all these variables are renamed so that there is no clash at all. So for all x, for all y1 not r x y1, or there exists y2 y2, or there exists y3 . And now I can simply pull out because these are different variables, right? And there is a disjunction, who cares, pull it out. So you will get for all x, for all y1, there exists y2, there exists y3, not r x y1, or I will push it in also. Oh, I think I missed some. So this is for all y, no? Pushing negation inside. I just forgot that I had to push negation inside. So this is for all, not, yeah. So this is for all. I missed one negation when I was writing, so not or. That's it. Yeah. So I've also written it as a bunch of disjunctions because we're going to see it in clausal form, right? So this will be helpful because this is already in. It's a bunch of disjuncts, and so it's in CNF. You can write it as clauses. But yeah. So this is one useful thing to have. We won't always. It's a useful normal form. Another form which I introduced last time and which is what we are going to discuss at greater length is columnization. Okay, so one is that every formula can be written in Prenex form. The second thing now is that we can scolomize formulas. What is columnization? Scolomisation is a way of getting rid of the quantifiers. This is this whole business of reducing first order logic to propositional logic. That is the. What does that mean? As I said, you take first order formulas and reduce them into Zoll formulas, zeroth order. So what do? So scolomisation is the process. So in general, if you have your formula, right? So let this be the leftmost occurrence of an existential quantifier, right? So it's the first occurrence when you read left to right. It's the first occurrence of. I am not saying it's in Prenex form, right? It's just that whatever is there, it doesn't matter, right? If you look at the first occurrence of the existential quantifier, this can only depend on all the earlier variables which are universally quantified before that, right? Now k in general is greater than or equal to 0. If k equal to 0, you replace this by for all x1, same thing for all x2, for all xk, alpha with y replaced by c, where c is a new constant. This idea of building in witnesses, it says there exists y alpha. For y, you substitute some new constant symbol. Yeah. If k is greater than 0, that means there are some universal quantifiers sitting in front of you. Then choose a k-ary function symbol, f, which is new, not occurring anywhere in the given formula, and replace this original formula by alpha with y replaced by f of, yeah. So this way you get rid of one existential quantifier. Now repeat this process. Yeah. So keep on doing that until you have no existential quantifiers. Now you have only universal quantifiers. Simply drop the and we have a Zoll formula. In fact, what you do is right, you have a zeroth order logic formula. It's got functions, lots of function symbols now, right? Because each time you see one existential quantifier like this, you introduce a new function symbol. So you've got constants, function symbols, terms, all this stuff, but then you've got only negation, conjunction, disjunction. We can assume that implications were already written anyway. So now convert it to CNF. So you have a clausal form. So this is usually what is called clausal form for first order logic. So you have a bunch of clauses and you write it as a set of atomic formulas or negations, literals, right? The idea being that what is inside a set is assumed to be disjunctions. So each set, and then so CNF means what? It's a conjunction. Each conjunct is a bunch of disjuncts, right? So that's typically how it's written. There's a message here. Okay. Yeah. So now, of course, it is not necessary for colonization to reduce to pre-next form and do it, right? You could take a formula given in pre-next form and do colonization, but it's not necessary to first to convert to pre-next form and then colonize. That actually might let me do a couple of examples and you can see kind of differences it makes. But is this process clear? Is what's colonization? Is that clear? Yeah, yes, Ananya, thanks. I think I see nobody else, so I don't know what people are thinking of anything I'm saying. Okay. So, yeah, so let me do a couple of examples and hopefully this stuff will be clear. Okay. So here is a there exists Z R X Y Z. That's all. So now first you are starting here. So this you can rewrite as for all y there exists Z R A Y Z. A is a constant, and now the next existential quantifier is here. So you replace this by R A Y f of y, right? And then simply drop the universal quantifier. In clausal form, you have exactly one clause. Yeah. So this is how you use colonization to convert formulas into clausal form. Yeah. So let me take another more detailed example. This has got lots of variables. I'm assuming I'm taking something in pre-next form, but yeah. So P of H of UV or QW and R of X of H Y Z. One horrible formula. Okay. Now, what have I got? I've got a U coming here. So this is the one that I have to change here. This is the only occurrence. So I drop this, change this into some constant A. Then the next is W. W is occurring here. That's the only place. And so I get rid of W by putting f of V. Now I have to, there is an X coming, and notice that X has to be a function of v now. So change this to g of v, and now I have a z which is dependent on both v and y. So I have h is already used, so I of v comma y, and now I get rid of these, and this is in clausal form. So I have two clauses, one p h a v q. This is one clause, and the second clause remember this is already in CNF, right? It's a conjunction having two conjuncts, and this has two disjuncts, this has one disjunct. Now this is how I did this. Let me go back to the same formula. Suppose I didn't actually do this blindly like I did. I should have kept it, I'm sorry. It was easier to just erase. There exists x for all y, there exists z, p of h of ub or q of w and r of x of h of y z. This is what I had. Notice that by the equivalences that I talked about, here if I look at this, x, y and z do not figure at all. So I could push this, there exists x for all y, there exists z right in here. And here again, if I look at it, uv is bound only here and w is bound only here. So I can actually push the quantifiers inside, and if I push the quantifiers inside, I get a different form. You will see that this is the same as, this is equivalent to, there exists u for all v, these two, p of h u v, or there exists w q w and there exists x for all y, there exists z, r of x comma h of y z. That's it, no? Some parentheses here. Now you see that the Skolem functions are very different. Here I just Kolemize this. I Kolemize this, what do I get? I get p of h a sum f of u. No. I just get p of h a v, right? Because a is the only one that I need to replace. After that, it's a universal quantifier which I can just draw. And then there exists w q of w will give me some q of b. Okay. And then here I get, what do I get? R C h y, and this is only dependent on z is only dependent on y. So I have yeah, that's it, f of y. If you don't want to repeat the symbols, call it some different things. Yeah. So in general, the Skolem functions will be much more compact if you push the quantifiers inside. If you have pre-next form, in general you may have greater rarity for your Skolem functions. Okay, and this may look very trivial for a formula like this, right? In general, when you are looking at a theory with lots of quantified formulas, it can make a huge importance. The size of Skolem functions can be quite nasty. Okay, so that's one remark. So what does columnization do for you? First, it gives it to you in clausal form, right? Now you can start doing your, remember I was telling you about resolution, right? Resolution as a rule of inferences with clauses, right? You take clauses and resolve. And I told you about DPLL, right? That works with things in clausal form. So all those algorithms for satisfiability, right, or algorithms for refutation, resolution based refutations, use formulas in clausal form. So for first order logic as well, you can take formulas in clausal form and you can start doing inferences. You can start doing theorem proving. That's why all this. So firstly, I think I mentioned this last time, I don't remember. Maybe let me repeat it, it's okay. First is, remember that columnization does not preserve validity. Okay, so this is not, it changes the meaning, right? So one should be careful about using columnization. And the example, this is the standard one. This is of course valid, right? If P of A holds, of course there exists X P of X holds. But the moment you scolomize, you get, let's say, P of A implies P of B. This is not a valid formula. Obvious, right? It's very easy to build a model where P of A is true, but P of B is false, right? So columnization does not preserve validity. What's columnization? Columnization does preserve satisfiability. So if what you are looking for is having an inference system, checking for satisfiability, perfectly fine. Or if you are doing refutation where you are doing unsatisfiability, it's okay. Yeah. So since you work with the opposite of the formula, right? So it does preserve satisfiability. So in general, if, as I said, just consider for all x there exists y alpha, right? If this is satisfiable, suppose this is satisfiable. Then after columnization also, you want to say that the preserve satisfiability, what does that mean? It means if you start with a satisfiable formula, after doing columnization also, it continues to be satisfiable. That's all we are saying, right? So if M satisfies alpha, what do we know? If and only if for every element D domain, there exists some D prime such that M with x assigned to D and y assigned to D prime satisfies alpha. But this is a for all there exists form, right? So this if and only if there exists a function f hat from D to D such that for all D belonging to D, M with x assigned to D and y assigned to f of D, f hat of D, satisfies alpha, right? This is what it means. There is some function on the domain such that whenever you pick D for x, f of D for y, alpha is true. This if and only if M prime satisfies for all x alpha with y replaced by f of x, where What is M prime? M prime is D with I prime pi, where I prime of f equals f hat. It's a new interpretation that you have to look at, right? It's not the same model, because now you have talked about alpha with y replaced by f of x. Remember, f is a new constant symbol, so it has to be interpreted. So I take the original old interpretation, I extend it to a new interpretation where I make sure that f is interpreted as f hat, and now it's easy to see that for all x, alpha with y replaced by f of x is true in the new model M prime. That's why this formula, alpha for all x, alpha with y replaced by f of x, is satisfiable. So if the original formula was satisfiable, the new formula is satisfiable as well, and you can reverse these arrows. If after scolomizing there is a formula that is satisfiable, there is a function, and therefore I can write that there exists x quantifier, right? So if for all x, alpha with y replaced by f of x is satisfiable, for all x there exists y alpha is satisfiable as well. So scolomization does preserve satisfiability as well as unsatisfiability. Yeah. So this is what is used in all the. So the point is, you start with a formula, scolomize, and you get it in clausal form. To check for satisfiability of the original formula, it suffices to check for satisfiability of the formula in clausal form. Now the clausal form formula is in CNF, right? So you can use exactly the original decision procedures that you were using. In particular, you can use resolution. Okay. So, and for doing that, but now there are a lot of, in the process you've introduced constants, you've introduced function symbols, you've got, all whole lot of stuff, right? It's not propositional resolution anymore. It's in clausal form, all right, but it's not propositional logic. It's all these variables, all these things are floating around, right? So how do we now do the original ones? So for that, you have this notion of what is called a Herbrand universe. So from now on, let's assume that, so the formula that you're talking about, S, which is a set of clauses, right? Instead of a formula, you are now talking about a set of clauses. These clauses are all atomic formulas, right? It's a set of sets, each set having a bunch of atomic formulas or negations of atomic formulas. And inside the atomic formula, you will have terms, right? This is the general thing that you have got. Now, we talk about, so let CS stand for the set of constant symbols occurring in S. If CS is empty, let's just make sure it's non-empty, that's all, right? If it doesn't have any constant symbols at all, pick one new constant symbol not occurring anywhere and use that, right? And Fn of S is the set of n-ary function symbols in S. Similarly, Pm of S is the set of m-ary predicate symbols in S. Okay. So then we define H0 of S to be, and Hk plus 1 of S and f of Tm, where and take H to be the union over should write H of S. So start with all the constant symbols, right? Those are all the initial atomic terms that you begin with, and then whenever you already have some m terms and f is a memory function symbol, form the terms with that, keep closing, right? That will generate all possible terms that you can have. Like for instance, suppose a is a constant symbol that occurs in S and f is a unary function symbol that occurs in S, then H will have a, f of a, f of f of a, f of f of f of f of f of a, all the possibilities, right? And then if you happen to have G, let us say a binary function symbol, and you had constants a and b, you would have a b, g of a b, g of f of a comma f of b, g of f of a comma g of f of a comma b, and so on. You understand, right? It builds all of these, and this is called the Herbrand universe of S. Is this clear? This is basically the entire language consisting of, you take the constant symbols and function symbols occurring in it, simply form the set of all possible terms with just this, that is all. That is exactly what it is. And the Herbrand base of S is exactly, Herbrand base of S is the set of all P T1 to Tm, Tn let us say, where P belongs to Tn and T1 to Tn belong to, and this is called the Herbrand base of S. What is the Herbrand base of S? It is all the, well, I should also put, yeah. Yeah. So for, it just says for predicate symbols, now apply the terms, you take the, from the Herbrand universe, plug in terms and form all possible n tuples that you can get. In general, this is going to be infinite, right? It is clear that this is always infinite. As long as there is one function symbol, right, you are going to have a, f of a, f of a, f of f. So if your S has, your clauses has any function symbol at all, remember you did Colonization. So if you had got for all x there exists y, that would have already introduced at least one unary function symbol, right? So the Herbrand universe, when is the Herbrand universe finite? When is the Herbrand universe of S finite? Sorry? You have only constant symbols. And when would that happen? If your clausal form had only constant symbols, there could have been, there would have been only outermost existential quantifiers. There was never any existential quantifier in the scope of a universal quantifier, right? So that is the only case. So that means what kind of formulas? If you had purely existential formulas, right, or if you had purely universal formulas, this colonization will generate a finite Herbrand universe. The moment you have any quantifier alternation, in particular something of the for all x there exists y form, right, your Herbrand universe is going to be infinite. And the moment the Herbrand universe is infinite, the Herbrand base is also infinite, where there are infinitely many terms and you plug in. Yeah, and this is reasonable if you think about it, right? Because it's only when you say for all x there exists y, you can start building in any kind of infinite sets, right? Because you start with an A forces you to consider, for instance, you want to talk about a successor, right? For every x there is a, for every m there is an n which is a successor of m. Well, if I start with 0, I have to build successor of 0 and then successor of 0 and so on, right? So if you had purely existential formulas or purely universal formulas, you do not have to consider infinite sets of terms at all. It is only when you start having for all there exists In fact, even there exists for all is not a problem, right? Because there exists for all when you scolemize will only give you constants. Yeah. So it's only when you start having something of the for all there exists form that the Herbrand base becomes infinite. Now you take any subset, let me write A subset of is called a Herbrand interpretation. Yeah, sorry, somebody.
One question regarding the Herbrand base. I don't understand the n-ary predicate. Why is it? What is n there?
N is the arity. Emery.
Would be. I mean,
A predicate symbol can have whatever arity, no? So you just put in that many terms. That's all.
so this the base is defined with respect to given n.
No. Each predicate symbol comes with some. So when I write PM here, you will have P0, P1, P2, P3, etc. Right?
Right.
Zero predicate symbols, which are just propositional constants, unary predicate symbols, binary predicate symbols. For each of them, you will have to plug in terms, right? For unary predicates, yeah.
So then, is it for all n?
So I am saying this is union over all of them, right? If P is an n-ary predicate symbol and you have written n terms, so this is just general notation.
Okay.
Yeah.
So overall.
Yeah, over all arity, right?
Okay. Fine.
Yeah. Similarly here also, this is over all arities. Binary function symbols will give you binary things here, ternary function symbols will give you triples and so on, right? So you will get all those terms, and then all those terms can be plugged into the next level, right? And so on.
Thank you.
Yeah. So, and what is a Herbrand interpretation? Herbrand interpretation is any subset. What is the idea? These are all the tuples made true in the interpretation. This is the standard term models that we have seen, right? We saw Henkin type models also. It's the idea is that, okay, one thing that I will assume now is that for the purposes of today, no equality in the language, because you have seen this before, right? When you take membership, this is the first thing we saw with if T equals T prime, right, is made true only if it belongs to the Herbrand base. We could think of equality as a predicate and plug it in, but then you have to make sure that it's a congruence, right? Then you have to make sure that if T equals T prime is in the interpretation, T prime equals T is also there. Then you have to take the transitive closure, you have to make sure that, so it can be done, it's a pain. It's the same idea, you have to take equivalence classes, work with equivalence classes and do this entire work. I'm afraid that's painful, so but this is something that we have seen repeatedly and I don't want to go over it again. So let's just assume that the language has no equality, right? And let's proceed with this. Now the way theorem provers actually do is, when you start with a formula, if it contains equality, what you do is, anyway you push negations all the way inside, right? So you have equality and inequality, T1 equals T2, T1 not equals T2, both will occur as atomic formulas. Propagate them inside. You rewrite the formula. If you have got T1 equals T2 sitting there, you rewrite the entire formula with, whenever you got T1, you can also put T2, put disjunctions. So you rewrite the formulas getting rid of equality. It's a bit of a mess, I don't want to deal with it. You can think about how you will handle equality when you're going to reduce everything into clausal form, right? So, but for today's discussion, let's assume that the language has no equality. Then it's very clear that now you've got an interpretation, and then you can say that this set of clauses is actually true under this interpretation. So we say A is a Herbrand model of S. This particular interpretation makes S true, right? Well, what is the idea? For atomic formulas, take any atomic formula, P, T1 through Tm, it's made true in the interpretation only if it belongs to it, right. Negation of an atomic formula, remember negation can occur only in front of atomic formulas, right. Negation of P, T1 through Tm is true in A if P, Tm is not there in the interpretation, okay. What about conjunction? Alpha and beta is true in A if alpha is true in A and beta is true in A. Alpha or beta is true in A, one of them is true in A. Anything else? Nothing else. There are no quantifiers, there are no nothing else, that is it. It's just Boolean, it just is all. So that is it. So now, this is the purpose of doing all these things, right. So, and these are the theorems that all this is for. Get rid of this. And this is actually quite straightforward theorem to prove. S is unsatisfiable that is, if S is satisfiable, that if S has a model at all, it has a Herbrand model, and if S does not have a model, no Herbrand interpretation will be a model, no Herbrand interpretation will make it true. This is actually quite straightforward, you just have to work through all the proofs. Like I said, I have already shown that if any formula is true, it has a model, then the Skolomized version has a model as well, right, same kind of ideas. Yeah. So, and this is a fairly straightforward. Now, whenever I have got a clause, I can talk about an instance of a clause. An instance of a clause is simply is one obtained by substitution of some variables by terms. Basically, you take a clause, it has got some variable x occurring in it, uniformly replace every x by t. Say x1 by t1, x2 by t2, you will get instances. And then you talk about a ground instance. A ground instance of a clause, of a set of clauses S, is a variable free instance. Particular kind of instances where what you have done is replaced every variable by terms, that means ground terms. What are ground terms? No variables in them, they are only constants and function symbols, right. So, you have replaced every variable by some constant or f of c, g of f of c, f of h of g of c, whatever, right, that is all that. So, you can think of this as a kind of solution. If you were to think of clauses as something like constraints or equations, the solution here is a ground instance. This is the terminology that it comes from. And now is the important theorem all this is leading up to. And this is a really beautiful theorem. Yeah. there exists a finite subset of S prime, finite subset S prime of ground instances of S So if you wanted to refute a formula, right, you write it in clausal form. Herbrand's theorem assures you that if your set of clauses has a refutation at all, then there is a finite subset of ground instances which will actually give you which is unsatisfiable. Okay, so this is a really non-trivial theorem, and some people call this like fundamental theorem of arithmetic and fundamental theorem of algebra. This is called the fundamental theorem of mathematical logic. It's a really non-trivial theorem. Okay, and if you're interested, I would be very happy to take up a proof of this. It'll take a couple of lectures. We'll have to do like we did for the compactness theorem. This is also, if you also look at it, this is the sort of compactness flavor to the argument, right? And but it's quite an interesting and difficult proof. Okay, the way to do it that I find most reasonable is to work through use cut elimination, turn it all into a proof theoretic thing, sequent calculus, and use cut elimination to prove. But we have not proved cut elimination either. That's the problem, right? So that gives a shorter proof. But Herbrand did. Okay, so this is also time to introduce another figure, right? And that is Jacques Herbrand. I think he's 1908, right? Yeah. Very colorful figure. All of 23 years, right? And yeah, so he died when he was 23 years old. And so he got his, did his PhD in École Normale Supérieure in Paris. His thesis, he submitted his thesis in 1929 and joined the army, and subsequently defended, I think next year, I think October 1930. These dates are very important because he defended his thesis in 1930, and his thesis was titled Consistency of Arithmetic, on the consistency of arithmetic. So what he was trying to do, the three figures that I mentioned, all were thinking about consistency of arithmetic. Gödel, Gentzen, and Herbrand. And they've had very different routes to thinking about it. And Gödel's paper appeared in 1931, right? I think I told you. This was in fact in 1930, September. You remember the very first lecture that I mentioned? Yeah. So around the same time, all these ideas were floating around. And in fact, the moment Gödel's paper appeared, Herbrand added another section to show that his results were not in contradiction with Gödel's theorem. Right? It's not obvious at all when you have a theorem of this kind. And he was interested in arithmetic. Entire thing was all to actually do all these proofs for arithmetic. And in any case, yeah. So, and then in July 1931, he went with his friends climbing in the Alps, and there was an accident. He fell down and died. So, and in such a short span of life, he wrote all his papers in 1929, 1930, 1931. There is a Herbrand Rebate theorem, which is also a very important theorem. This is on cyclotomic fields, p-adic integers, and class field theory, fundamental theorem. which is the form that was used by Andrew Wiles for proving the Iwasawa theory and so on. So, another fundamental contribution of Herbrand, and then this Herbrand's theorem, which, as I said, many people would call the fundamental theorem of mathematical logic. And I think a couple of other things, I don't remember, maybe I've noted down here. Yeah, he introduced general recursive functions. So it's not these Herbrand universe, the way it is set up, as you can see, there is like a level of recursion that you can actually define for every term, and this is what was very important and useful for people who came later on to set up general recursive function theory. So he did a lot of work in a very short span of time, and in his thesis he proved consistency of a weaker system of arithmetic than not Peano's axioms or Peano's arithmetic. So yeah, all this is to only advertise in case you are interested in Herbrand's theorem, but that's a lot of work for taking up. But just to assure you that all this business of columnization, reducing it in clausal form, and then running after it, the theorem provers are actually following Herbrand. And I saw one very nice quotation where Richard Courant says that when he's criticizing Bourbaki, he says Herbrand would have hated Bourbaki. So that is his, because Herbrand was, he believed in intuitive proofs. He hated this style of writing proposition lemma and so on. But then in the process, he also had made mistakes. There is one bug in his proof which was fixed, pretty easily fixed. Probably he would have fixed it very easily himself. But he wanted mathematical writing to be, easily communicable. Very difficult proofs should be written using intuitive explanations and so on. He didn't like the Bourbaki formal style at all. So it's very important because he was talking entirely about formalization, but he didn't want to use formal. I mean, he hated the Hilbert style system kind of proofs. So his thing is all very different, as you can see. So all this clausal form, unification, these ideas go back to Herbrand. Basically, that's the. But what is amazing is that his insight turned out to be the most useful thing for all these software trying to prove theorems. Yeah. So, of course, he intended it for human beings. That's my point. He didn't. I don't know. Who knows what he intended it for? But anyway. So here is an example to show you how this business works. I mean, the kind of thing you want to reason about. Trivial example, right? For all x px and for all y py implies qy, then qa and qb holds, right? And the thing is, you convert it into clausal form. This one will give you the clause px, and this one will give you not of py qy, and this one will give you qa qb. And now you take the ground instances, you're going to get PA, PB, the two constant symbols you've got, and not PA, QA, not PB, QB, QA, QB. Yeah. So, and now you can resolve these two and get QA. Yeah. And yeah. Oh, that should give you not QA, not QB. So that was a mistake. In clausal form, when I write this, right, I'm going to get, I'm taking negation of this, right? This is not P or Q. So this and negation of this. So I'll get not QA, not QB. I was wondering why I'm, yeah. So this is okay, this is good. Yeah. So you take ground instances like this, you resolve those two, you will get QA. You resolve these two, you will get QB. And then you have got not QA, not QB. And this is clearly unsatisfiable. And this is, in fact, the intuitive proof of Herbrand's theorem. The point is that you can always do it, is what the theorem says, right? That you can find a finite subset of ground instances from which, by substitution, you can resolve. As I said, resolution is something that Robinson gave later, but it's based on the proof idea of Herbrand's theorem. That, and then you refute this, use the clausal form, and then keep resolving until you get the empty clause, and that's a sound inference rule, is what this is. And yeah, so this is our, in the Hilbert style system, this is really how we proceed, right? From this, somehow, from for all x px, we infer pa and pb. Pa and for all y, py implies qy gives you qa. Pb and this together gives you QB, therefore we infer QA and QB. This is how we would be doing it in either in the Hilbert system or in natural deduction or any of them. His point is that by taking refutation to show that this is valid, you just show that if I take this and the negation of this, that is not satisfiable, and for that you take that, convert it into clausal form. You can use ground instances, and the ground instances are all inspired by the given formula. This is what we are using, right? You start with some set of clauses and build a Herbrand base based on the clause, what the clause mentions. This is the important thing. And of course, in the process of getting rid of quantifiers, you introduce function symbols. But those function symbols capture the dependencies that your logic, your formula originally had, right? The critical thing that first order logic brings in here, the rest of it is propositional, is the quantifier alternation, right? It's a quantifier alternation that is bringing in the dependencies, and that's plugged into your formulas using your function symbols. Now, the moment you have got arbitrary terms, how are you going to combine them? This is a very simple example where I had only constant symbols. In general, how do you do it? And that's the complicated part. All the work is on that. And that's the process of unification. And unification is exactly what Herbrand introduced. He gave the unification algorithm. Okay. And so, what is the first order resolution rule? I think I have already introduced this. If you have got clause alpha beta 1 through beta m and not delta gamma 1 through gamma n, you can resolve these to get beta 1 through beta m, gamma 1 through gamma n, if there exists some sigma such that alpha sigma equals delta sigma. Yeah. So you can use some substitution. Under some substitution, these two are contradicting each other. That is the idea. Under some substitution sigma, I get the same here, and this is a negation here, therefore you can resolve and get the rest. You can throw away that and continue. And when you keep doing that, if you get the empty clause, you have done. So this is the process of unification. So this is the unification, is the operation of finding a common instance. Remember, these are both instances, right? Alpha, oh, I'm sorry, what have I written? Yeah. Either I should write it like this or under sigma, what have I written, alpha? Yeah. Under the substitution, they both give the same formula. That's what I want to say. Okay. So, finding a common instance of two or more terms. It's the terms that need to be unified, right? Like I had A and B here, these were the terms, but in general you're going to have some complicated terms. So let's just see these. Yeah. So for instance, so let me take the examples here. So let's assume that A and B are distinct constant symbols. So suppose I have got f of xb, f of ay, right? I can obviously substitute x by a, y by b, and I will get f of ab as the common instance. So that's I can unify these two terms by a substitution a for x and b for y. But this is not the only one. For instance, suppose I have got f of x, f of ab. Is there some, there is no common instance at all. Yeah, because if I substitute x by a, I cannot substitute x by b as well, right? This is a map, it's a function from variables to terms. So these two terms are not unifiable, that's what you mean. Similarly, now let me write, suppose I have got f of x, f of y, g of y. What about this? Well, x has to be unified with y, I mean x has to be substituted by y, that's okay. But then x has to be substituted by g of y, that means y has to be equal to g of y, where y is a variable. Now what kind of a term can you have? That means you have to have a term like g of g of g of, yeah, that's an infinite term, and we don't have infinite terms in the syntax, right? Of course you could have infinite terms instead of terms as trees, like I always said, right? You could think of terms as infinite trees and do the job, but that's a different game altogether. We don't have that. So these two are also not unifiable. So and this is at the heart of unification. Let's so in general you can substitute only for variables, right? Substitution is a map from variables to terms. You can't replace, I mean constant symbols are constants, right? So you can't change them. And function symbols, they are function symbols. You can't substitute f by g, right? F is a different function, g is a different function, right? You can't substitute where plus comes, you can't turn it into, addition into multiplication, right? So you can't do all that. It's only variables that you can, x is a variable, you can give it a value 3, there is no problem. You can give it a value g of 3, right? That's also okay. So this is the sort of thing that we want to. So in general, your map theta is a map from variables to terms, and typically it's written as the graph of the function, right? You write it in this form. X is given a, y is given b, etc., etc. It's a partial function from variables to terms, and the typical notation for this is postfix. So you write t theta to talk about applying the function substitution theta on the term t. T theta is the result of replacing this, and that's, you can define inductively. C theta is C. Take a constant symbol, do any substitution, it will get you the same thing. X theta is T, where theta of x equals T, and then f of T1 to Tk theta is f of T1 theta Tk theta. Similarly, P T1 through Tm theta yeah. So you go inside and apply. The important thing to, and then you have clauses alpha 1 through alpha m theta. So basically you are only applying it on terms, and so now you can talk about instances of clauses under substitution theta as well. Remember that when I am doing this, the application is being done simultaneously for all the variables. Like for instance, if I have got this is the notation that typically is used. X is mapped to the term hy and y is mapped to the term b, then this does not mean x is mapped to hb, right? No. Wherever x comes, you replace it by hy. In the original term, right? If you see x, replace it by hy. If you see y, replace it by b. It doesn't mean that you apply this further. All the applications are simultaneous. Okay, so let me just, it's already so much time. Show you some again examples. So so let me take this theta as this. F of x gu y theta. What is this? F of hy gu b. Right. So this x is being replaced here. This y is being replaced by b. This is to point out that predicate symbols also I can apply. I will get the same thing, and this h, so will generate h of hy z for a clause px not qy theta, replace everywhere. Yeah, and so the idea is that now you can start looking at instances, and an important one is that these things get composed, right? If rho and theta are substitutions, so is rho composed with theta. And this is what is T of rho composed with theta, that is T rho of theta. First apply rho, look at the resulting term and apply theta in that. So for instance, if you had rho is jx y0 and theta is z, some cooked up stuff. But the main point is that when I now do rho composed with theta, what will I get? Remember, I first apply rho, and then on the resulting one, so u will be replaced by j of h of z, yeah, and x is going to be replaced by h of z, there is no change. And what about y? What will y get? I first apply rho, and on the resulting substitution I am applying theta, so 0. Yeah, the g of 3 is all eaten up. Yeah, so and this thing is important because well, okay, now we say that theta is a unifier of you apply theta and all the resulting terms turn out to be identical. There is a way of substituting, finding common instances. Like I was saying, common instance, right? Like f of xy, f of xa, and f of by or whatever, right? And so that's a unifier. And what else? So in general, they must have some similar structure. That's what we are saying, right? And so Now, one example at least before I stop. Suppose I have got two terms, g of x and g of y, right? I can, yeah, no reason at all, x is replaced by 3 and y is replaced by g of 3. This is a unifier because I'll get g of 3, right? This is one unifier. Here is another unifier. And y is, yeah, I replace x by z and y by g of z, and I get a common instance g of z. So this is also a unifier. And x by g of u and f of u and y by g of f of u. This is also a unifier because I'll get g of f of u. Okay, and here is one which is probably what anybody will think of. Replace y by g of x, right? That will give you the terms g of x, right? So this generates ground instances, right? These don't generate ground instances, right? That is the difference between these. So in general, so somehow we would like to say that this is more general than all the rest, right? This is the most economical substitution in some sense, and that's the idea of something being more general. We say that theta is more general than sigma if, then let's say rho, if there exists some sigma such that theta is more general than rho if I can always find an additional substitution, a later substitution that generates whatever you have given me. So in this sense, it's easy to see that theta 4, the last one, is more general than all the rest. Let's see why. Theta 1 is theta 4 composed with whatever we have got, x gets 3, right? And what is theta 2? Theta 4 composed with x replaced by z. And theta 3 is theta 4 composed with x getting f of u. And what about theta 4? Theta 4 is theta 4 composed with the empty substitution. So one consequence of this definition is that every substitution is more general than itself. So it should not be, we are used to greater than or equal to, greater than or equal to, and so on, right? So we should actually be saying more general or equal to, but people don't say it, they just use a simpler term, that's all. But yeah, so, and another thing to note is that okay, so from this you have the definition of, we say theta is a most general unifier of T1 through Tm if theta and for any unifier rho of T1 through Tm, theta is more general than rho. This is the natural definition you will think of. And what do I say? A most general unifier. Well, you can see that two substitutions could be identical by simply using different variable names, right? Here, if I am writing y, I have used z here. Suppose I have another substitution, theta 2 prime, which is x by u and y by g of u. They are both identical substitutions, except that up to renaming of variables, right? So you can have two different most general unifiers for a set of terms, but they are identical up to variable renaming. Yes, so it's unique up to variable renaming. So that's why you have to say a most general unifier. It's not the most general, right? And yeah, what else? So an important observation. I'll finish with that. Suppose x occurs in T. Then there is no theta such that this should be easy to see. You suppose you substitute x is actually sitting inside T. T is a tree and x is sitting somewhere inside that. Now suppose you actually substitute x by another term T prime, right? Now what will happen? You go inside T, you substitute that. Remember that now I am putting T here, that will generate an x, right? This is exactly what happened with y and f, g of y, right? The moment I put g of y, I will have to have a term which will be g of something, g of something, and you will get an infinite subterm which is not possible, so you can't have. So when you are trying to check if two terms are unifiable or find the most general unifier, if it exists, an important thing is to check whether you are trying to unify, you are taking a variable y and trying to substitute it by a term t where y is already sitting there. You can't have that. If you take a variable and try to substitute it by a large term which has got y sitting inside it, you won't be able to find the unifier. This is the important. So now the idea of the unification algorithm, which is what we'll look at next time, is find a MGU of if it exists. Obviously, as we have seen, terms need not be unifiable. So if there is no, if they are not unifiable, you must say no, they are not unifiable, and if they are unifiable, you should be able to find the most general unifier, find a most general unifier for all the terms. Once you have that, you can plug it into the resolution procedure, and that's it. After that, you can churn out your theorem provers, and this is pretty much what you will find, that whatever I said for DPLL resolution, everything lifts to first order resolution with just this addition of the unification algorithm. Okay, so I'll complete this next class and move on to other topics. So you might as well think about how your the unification algorithm will go, right? Think of just two terms. How will you come up with the most general unifier of two terms? Think about it. It's not very difficult, quite straightforward really. Okay.